Around 1850, Corliss replaced in many textile mills the old steam engine by one of his design, and realized fuel savings from 30 to 50%. Main reasons for this fuel economy were: 1. Very small clearance space between valves and cylinder minimizing steam losses. 2. Short cutoff saved fuel due to expansive use of steam. 3. Reducing wire drawing of steam and keeping steam pressure above piston at almost the boiler pressure to the moment of cutoff. 4. Governor controls duration of steam admission instead of the opening of the throttle valve and its unavoidable wire drawing. Let's take a closer look to engine cylinder and its steam admission and exhaust valve. Typical for the Corliss engine are the valves which rock about their long axis and the use of 4 valves per cylinder. Their advantage was to provide better control of valve events than the more common single slide valve. Another advantage was the very short passages between the valve and the cylinder. The shorter these passages, the more steam and thus fuel is saved. The cycle of an engine using the so-called expansive work of steam is the following, focusing on the upper valves. Admission. The upper exhaust valve has just closed. The upper steam valve has just opened, and steam rushes into the cylinder and begins to push the piston downwards. Cutoff. The upper steam valve has just been tripped shut at a point determined by the governor knockoff bar. See later. Expansive work of steam. Upper steam and exhaust valves are closed, and the piston is now being pushed only by the expansion of the steam. The steam pressure above the piston decreases, illustrated by the darkening of the red color. Exhaust. The upper exhaust valve now opens to allow the expanded steam to escape to the condenser. The pressure above the piston decreases to the vacuum pressure in the condenser. James Watt thought about the concept of expansive working of the steam with the object of saving fuel. He experimented with this concept, but it did not prove practical due to the low pressure of steam then in use because of boiler pressure limitations. The value of expansive working of steam was first widely demonstrated by the Cornish engine. In a conventional system as represented on Figure 4, as the engine's speed increases and balls E fly outwards by the centrifugal forces, fork F moves downwards and the valve Z in the steam pipe from the boiler to the engine turns counterclockwise, thus closing partially. The steam supply is choked off and the engine slows to its nominal speed, and vice versa when engine speed decreases. This mechanism is called a throttling governor, and steam choking leads to a less efficient engine while the steam pressure on the piston is unnecessarily lowered beneath the boiler pressure. Another problem was that the governor had to shift the valve against steam pressure and friction, rendering it sluggish and slowly acting. Another requirement for an effective engine was for a quick and efficient control mechanism. So George Corliss invented the so-called variable valve timing and patented his idea in 1849. This invention made his engines up to 30% more performant than earlier steam engines. For a better insight on how the engine works, we will make only the moving parts of a single engine visible. All starts with the eccentric. This is a small wheel mounted off-center on the shaft. As the shaft tums, this eccentric drives the eccentric rod, the valve stems, and finally causes the valves itself to turn around back and forth. A bevel gear on the crankshaft and a horizontal drive shaft makes the governor to spin about its vertical axis. This is a more reliable and precise setup than the conventional belt and gear drive. The valve gear, patented by Corliss in 1876, was a modification of his grasshopper type and was, as far as known, unique to the Centennial Corliss engine. There are 3 curvaceous bell cranks like plate D, also called wrist plates, the form of which, said the engineer, strikes the eye as being peculiar. The advantage of these wrist plates B, C, and D was that the angularity of its connections modified the speed of the valves, such that the valves moved quickly while covering or uncovering the ports and slowly at other times. The exhaust valves are solidly connected to the wrist plates and thus stay open or closed through most of the stroke, but the 2 steam admission valves are attached by a mechanism called the trip gear or releasing gear. The dashpot acts in fact as a spring. When the plunger is lifted by the steam valve lever, a vacuum is created underneath its lower part. When the lever is released by the trip gear, atmospheric pressure pushes the plunger downward, thus closing abruptly the steam valve. An air cushion under the upper part of the plunger dampens this movement. Plate F is connected to wrist plate D, which is also solidly connected to the exhaust valve lever E. Trip gear lever J connected to the dashpot, and the steam admission valve is forced against plate F by spring K. The governor knockoff bar is connected via a series of levers to the governor. Should the load of the engine decrease, its speed increases. The governor's weights are pushed outwards by higher centrifugal forces, and by the connecting levers, the governor knockoff bar moves to the right. When the piston is at the top of the cylinder, plate F starts rotating upwards, entraining the earlier engaged lever J and opening the steam admission valve. However, because the knockoff bar has moved to the right, it pushes the lever J off the wrist plate a bit earlier. The disengaged valve rod closes abruptly under influence of the vacuum created by the lift of the plunger in the dash pot at an earlier point in the stroke of the piston. Less steam is admitted to the cylinder, and the engine slows down to its original speed. It was hard to find any information about the installations in the cellar under the platform of the Centennial engine. But an Austrian governmental commission visited the Centennial Exposition in Philadelphia, and Ratinger, professor at the Technische Hochschule in Vienna, wrote a report on the United States steam engines exhibited there. Based on a scheme in this book, we reconstructed as far as possible the installations beneath the platform. The main steam line to the engine was 18 inches or 0.46 meter in diameter, and 320 feet or 97 meters long, insulated with felt. The two steam stop valves could be operated from the platform. The boilers were cylindrical, vertical Corliss boilers, 20 in number, capable of 80 pounds per square inch of steam, and each reckoned good for 70 horsepower. The boiler feed water pipe brings warm water from the hot well under the condenser to the boilers. The condensers are water jet type condensers. Cold cooling water is brought to the condensers through the two platform-operated handwheel control valves. Lifting or lowering the spray control rod controls the dispersion of the spray droplets. The warmed-up water is collected in a reservoir underneath the condenser, the so-called hot well, which is connected to the air pump and the boiler feed water pump, both driven by the beam through rods. The required quantity of cold cooling water is much larger than of condensed steam. All that water, together with some parasitic air entered through non-perfectly airtight stuffing boxes, joints, etc., has to be pumped up and brought from vacuum to atmospheric pressure. This is realized by the typical Corliss air pump. Some warm water is pumped up out the hot well by the boiler water feed pump and brought to boiler pressure. A cylindrical partially with air-filled damper flats out the pressure pulses, and an overpressure valve limits the pressure at the outlet of the pump. The power distribution system from the engine to the many machines exhibited throughout the hall comprised 183 tons of gearing and shafting beneath the floor, which was provided by Corliss, plus nearly a mile of overhead shafting and belts provided by other contractors. At the ends and at two intermediate points on this shaft were 4 nests of bevel gears. Each nest had 3 bevel gears. These bevel gears drove 8 shafts under the floor, reaching to the sides of the transept. There they drove belts at 8 places, reaching up to drive the 8 overhead shafts. They had numerous pulleys on them from which belts drove the individual machines. This whole system was similar to that employed in factories at that time. The engine was designed for a speed of 36 revolutions per minute at a steam pressure of 25 to 80 pounds per square inch, giving an indicated horsepower of 1,400, with a possible maximum of 2,500 indicated horsepower. But at the exhibition it was running with only 10 psi of steam and a very short cutoff, realizing no more than 400 horsepower since so few machines were actually working. Anyhow, its size and quality of workmanship translated after the exhibition into 29 years of reliable service at Pullman's factory under an average load of 1,400 horsepower and with a very good efficiency, as it was designed for by George Corliss.